configuration. All right, and so here's the structure. Structure looks like this. So that's the number one. Alright, so we have two there for you. Let's see if you can name them correctly using IUPAC and absolute configuration. You know, absolute configuration is RNS. For the people that are just arriving, all I'm doing is making sure that I have the full class before we start the new chapter, which is chapter 6. That's what I'm trying to do here. We're missing quite a few of you. I know. That's what I've been told, that the traffic is just horrid, so that's the reason why I'm holding off on starting the new material. I know the traffic, listen, I can see why people would like to go and move to an area where you don't deal, this is stressful. You know, when you have to get to a class and you think you have allowed yourself all the perfect time in the world, and then you deal with this, that is stressful. We live very stressful lives. All right. The other classes, you ask us to do something and then you don't give us enough time. That's what they accused me this morning. So I'll be quiet.
One on three. One, two. You get this. This is right, one or three, right?
I don't know. I haven't even spent time with it.
Oh.
I guess I should. Okay, is this enough time for everybody? Let's try. Okay, my recommendation is that you start with something that you know, right? And what I know is that when numbers are equal, that's gonna be 1, 2, 3, or 1, 2, 3, right? That when numbers are equal, then the deciding factor is then the alphabet of the substituents, provided the substituents are equal in priority. Okay, so far, your substituents are equal in priority when numbers, after you've established the parent, right, cyclohexane. So after you've established the parent, when numbers are equal and the substituents are equal in priority, then what is important is the alphabet. We would have chloro, we would have iodo, so I think it goes without saying that the beginning of the name is gonna be the 1-chloro, and then 3-iodo cyclohexane. We're moving into the alkyl halides, so you can see already that naming alkyl halides, we know. Alkyl halides, the halogens, that's what we're gonna be doing. So if you only have this, obviously you have not even paid attention to the stereochemistry of the compounds, right? In the case of carbon number 1, your first priority is chlorine. You're looking to find the second priority. You don't see it on carbon 2, so you have to go further, and you see it on carbon 3. So that will be priority 2. At the top is 3, the lowest is in the back, so you're going R and you stay. So 1 should be R. Did everybody get R for number 1? Yes? All right, very good. When I look, yes? Okay. When I look at carbon number 3, I'm doing the exact same thing. The first priority should be iodine, and the last one would be hydrogen. So whatever it is, I'm going to assign and switch, because the lowest is in the front, okay? So priority 1, when I look at the second priority, they're both the same, so I have to go 1 carbon further. When I get to that carbon further, the one that has the chlorine should be priority 2. Then over here is 3, so you're going counterclockwise. So this is what I write on my papers. So this is S, but no, you're R. And then I switch. So then 3 is R, and then my whole name, for you to get all the points, it should be parentheses, 1 capital letter R. The letter is in capital letter, comma, 3 capital letter R, close parentheses, hyphen, 1-chloro, 3-iodo cyclohexane. How many people had this correct? Excellent, excellent. All right, we take a look at the Fisher projection. And at the Fisher projection, every time you see the vertical line, this is really telling you that this is perhaps the body of the molecule, right? So this is the length of the whole molecule. It doesn't necessarily have to be from there. You could have started numbering from the bottom, right? So you could do either one. When you see that you have the horizontal line, that horizontal line is representing that there are 2 chiral carbons. So the only time that you're doing that horizontal line is to represent that that carbon is chiral, all right? So the carbon is chiral. Again, we do what we remember, and what we remember is, okay, this is carbon 1, 2, 3, 4, 5, 6. So I would have on carbon 2, I have the bromo. On carbon 3, I have the chloro. And I think I counted 6, right? 1, 2, 3, 4, 5, 6. So it is hexane. Again, that is just a basic. That shouldn't give you any points, but you know, perhaps I will give some points. We really are looking at the absolute configuration as well, right? So we do the exact same thing. We having to assign priorities. Bromine will be priority number 1. When you go 1 carbon away, that carbon has 3 hydrogens. Well, this carbon only has 1. That should be really easy to then decide that down here is priority 2, and at the top is priority 3. So you're doing that, which is R, oh no, but you're S, because you are on the wedge. Okay, I'll do it again. I am priority 1, down below your priority 2, and at the top you're 3. Is everybody seeing that or no? Everybody okay? So it's like you're going that way, so you're going R, but no, you're S, because you're on the horizontal line. If your lowest priority is on the horizontal line, it's really like you are on the wedge. So just like we did above, if you're on the wedge, you assign and switch, just like we did above when you were on the ring, okay? Exactly like we did above, like you were on the ring. So to this name, I would have to already add what, sorry. So that name, I would already could add 2S, right? So I could add that as the 2S for the beginning of that name. Okay, when I look at carbon number 3, now your priority one should be your chlorine. When you're looking for priority 2, you're like looking at one carbon away, right? When you look at this carbon has 2 hydrogen, this one only has 1. That should immediately be a giveaway that you have more other attachments. So up at the top is 2, down below is 3. Now you're going R, but you really are S, everybody, but you really are S, because you again had the lowest on the wedge. So the name for this compound is 2S, 3S, close parentheses, hyphen, 2-bromo, 3-chlorohexane. How many people had that name right? Okay, so the other students that did not have it right, can I explain anything differently? Can I say something to help out? Nothing? Fine. Nothing I can say that can help. All right. What is the enantiomer of this?
2R, 3R.
Enantiomer of that one above? The enantiomer will be 2R, 3R, right? Is everybody there? Okay, what is a diastereomer? Diastereomer of that one. What could be a diastereomer of that one? 2R, 3S. I hear 2R, 3S, I heard that. Is that correct? Sure. You keep one the same, you switch another one. Is there another enantiomer, another diastereomer?
2S,
Yes,
3R.
2S, 3R. Is everybody there? So, here comes a handy little formula, and the handy little formula is 2 to the N, where N represents the number of chiral carbons. Okay? The number of chiral carbons. N represents the number of chiral carbons. In the structure above, you had 2 chiral carbons. So you could have 4 maximum number of stereoisomers. Okay, so 2 to the N equals 4 is the maximum number of stereoisomers, is what this is saying. All right, so do we have the 4 stereoisomers? Well, yeah, is everybody seeing the 4 stereoisomers? The original molecule that we gave you, which is the 2S, 3S, it's an enantiomer, 2R, 3R, and it's diastereomer. So you have 1, 2, 3, 4 possible stereoisomers for that compound. Is everybody okay? So if you work, go ahead.
So if you have no chiral centers, there's no stereochemistry.
That's right. You need to have a chiral carbon in order for you to have stereoisomers. If not, there are some exceptions. There's like 2 of them that it's not quite like that. So one exception is double bonds, which are allenes. But for the rest of it, you have to have a chiral carbon. Okay, we have more students now that have arrived. I would assume that this is possibly the entire class unless somebody else is still falling so far behind with the traffic. I said at the beginning of the class that today is our last day to really put stereoisomer chemistry together. When we go into discussion, we're going to do the 2 discussion packets, the 2 sheets of discussion that are applicable to this. The afternoon is total dry lab, where you really are looking. I'm sending you to different web pages, giving you some work to do to get it. Everybody should be able to do this. So, no problem, I did not grade the lab notebooks at all. I'll hand them to you so you work, you'll hand them back to me again, trying one more time to get it done. And I really need to start chapter 6, is what I'm saying. So, we're gonna start chapter 6. Chapter 6, I'm using your PowerPoints only because I can go faster, until I need to slow down, okay? So I'll go faster until I need to slow down. The very first thing is that we're gonna be looking at your alkyl halides. And we're gonna be looking at the chemistry of this, all right? So the first thing that happened is that we have to know how to classify alkyl halides. Alkyl is the carbon, there's the halogen. So take a look how different they all look, right? Is everybody seeing how different they all look? You have a Br bonded to an sp3 hybridized carbon. You have a Cl bonded to a carbon-carbon double bond. And you have an iodide bonded to an aromatic. Okay, these are the distinct 3 different types of alkyl halides. Alkyl halides are this. The halogen is directly bonded to an sp3 carbon. That is the chemistry that we are to do this semester, okay? So this is, for us, what we are going to learn, all right? This is us, a little star, this is what we're doing the whole entire chapter. So if your carbon is not sp3, you do not touch them. Everybody? You're not touching any carbon that is not sp3. All we're doing is we're identifying it, all right? So we're identifying it. Over here, when you have a halogen bonded directly to a carbon-carbon double bond, that is called a vinyl halide, and your halogen is bonded to that sp2. We're not doing any chemistry with that at all. And the last type of alkyl halides, or the last type of halogens that we know, are called aryl halides. And aryl halides are bonded, halogens bonded to an sp3 carbon on a benzene ring. This is Chem 4. The chemistry of these guys is Chem 4. But nonetheless, what do you have to do in this chapter? If I give you an example, you should be able to classify it. That's what we're trying to do here. So yes, you need to know what is a vinyl halide, what is a aryl halide, but the chemistry of these two, chemistry of these last two, we're not doing in this chapter. All right, we continue on, and one of the reasons of explaining this chapter is that all of these compounds, alkyl halides, have a polar bond. And that polar bond allows anything, see how that carbon is partially positive? So because you have this polarity, okay, that polarity allows us to do a lot of chemistry at that site. All right, so a lot of chemistry will be done at this site. We do know that the halogens are more electronegative than the carbon. We know that the carbon-halogen bond is polar. And we know that that partial positive charge is what's going to allow me to do chemistry at that end. Okay, so for order to me to do chemistry at that end, and you need to have somebody that is a nucleophile. Do we remember what a nucleophile was? What was a nucleophile?
Lover of
Lover of nuclei,
yeah.
but for me, a nucleophile is either a molecule with lone pairs, right? So we can also draw your nucleophile like this. Your nucleophile can be somebody like that. We're going to call it Nu with a dot dot. And Nu with a dot dot, you can see immediately that this is a molecule, right? And Nu with a dot dot, this is a molecule. Or your nucleophile could be an Nu with the dot dot and a minus. Then we're looking at what? At a negatively charged ion, right? So if you're looking for examples that you would remember, I think the comparison here will be water versus hydroxide, you know, to keep examples of that, which we're of course going to use them in its entirety. I don't think, okay, and then the halogen would be the leaving group. We don't even want to get into that. IUPAC nomenclature, I don't think I need to do anything, but we're going to go quickly through the compounds. They're gonna be called halogen, yeah. What are you gonna name that one, like if you need to know that? What would be the name for that one now?
2-chlorobutane.
Everybody knows that you're gonna find the longest chain, that you're gonna give it 2-chlorobutane. For me, the only reason why I'm showing this example, because now I have an extra layer, right, an extra layer. And that layer is taking a look at that carbon. Would you say that carbon is chiral? It's not drawn. It's not drawn in a way that you can say is R or S. Everybody, the way that this is drawn, this is its name. So I don't have it in wedges and dashes or fissure, so this is its only name. But I know in my head that that carbon has 4 different groups around it. So everybody, that's how we want to think of this now. Okay, that's our new higher level of thought. Okay, higher level of thought, not drawn for me to do anything other than that, but I know that that carbon that has the chlorine has 4 different groups. So that is a chiral carbon, regardless if it's drawn or not that way. All right, very good. When I come over here, let's see what you can do with this compound. How would you name this compound? And I do like this example. We would look for the longest continuous chain. If I go this way, I have 1, 2, 3, 4, 5, 6, 7. If I go this way, I have 1, 2, 3, 4, 5, 6. Or I have 1, 2, 3, 4, 5, 6. Guess what? You have to go the longest route. Is everybody? So even though the fluorine is there, they're not that important. All this is saying is that even if you have a halogen hanging off, you do not have to start from there. Okay, when we get to the alkenes, if you have a double bond, even if the length is like this with the double bond, and you could go that way, some other way, you have to take the double bond and make it part of the chain. Okay, so say it again. When naming alkyl halides, you still look for the longest continuous chain, okay, even if the halogen is not in it. All right, so even if your halogen is not part of the longest chain, it doesn't matter. You take the longest chain to be the parent. Because these guys are only substituents. They are named just as substituents. So how are we going to name this guy as a substituent? What is the point of attachment? Right there, right? Right there. And so this would have been what? An ethyl, right? Without the fluorine, this would have been an ethyl, but now you've put a fluoro on carbon 2 of the ethyl. So then it looks like that. Point of attachment right there. What would be the name? Can you see it? Can you spell it in your head?
4 parentheses, 2-fluoro, heptane.
So everybody, so you would do 4, the point of attachment. The 4 is the point of attachment where you attach two groups. And then at that moment, your fluoro is on carbon 2, and that became 2-fluoroethyl heptane would be the name for that one. Okay, as we continue on, I mean, we've done these already, I'm not even gonna go there, right? So everybody, I don't think I need to go through all this, right? So let's take a look at this, and the reason why we're gonna take a look at this is because these alkyl groups, we still have to remember them. Does anybody remember what that one was called? Old historical nomenclature. This one was what?
Sec-butyl? No, I mean,
This one was isobutyl, right? That one was isobutyl. So when you see two words, like isobutyl bromide, 2 words, that's old nomenclature that we still want you to remember these pieces. Okay, this one was the sec-butyl, and that was the tert-butyl. Okay, so that's old nomenclature that even your PowerPoint, all the books are saying we're not giving them up. Okay, it's just not given up. New nomenclature, so easy, right? New nomenclature, so easy. This one would be called what? Back over here. New nomenclature, what would this one be called? 1-bromo, 2-methyl propane. Yes, yes? Okay, everybody again with me. So new nomenclature, that will be your carbon 1. Did I name those? No. New nomenclature, that will be your carbon 1. So that'd be 1-bromo, 2-methyl propane, right? If I look at this one, what will be its IUPAC name?
2-bromo.
Who said?
Two.
Dean. Yeah. Dean says, no, you're just gonna go like that, the longest. So it'd be 2-bromobutane. You're looking for the longest chain. Don't forget what you already know. Okay? So for the isobutyl bromide, the longest chain was only this. Right? So for the isobutyl bromide, the longest chain was that. But for the sec-butyl, the longest chain is this. Right? That's your longest chain. So then the bromo is on carbon number 2. For the tert-butyl, the longest chain is this way. And then this one would be your 2-bromo, 2-methyl propane, right? 2-bromo, 2-methyl propane. Is everybody okay? But we still remember the tert, the sec, the isobutyl. Some of the common names, you've seen some before. We have to memorize them because they're used in the labs a lot. Thankfully, you have used methylene chloride already. Remember that? Some of you are looking at me like, no. You used methylene chloride in the lab of extraction. I don't know if you remember, but the methylene chloride is the one that you use. It was CH2Cl2. So that is a common name that you have learned already, that you have to remember always. And that is a common name. IUPAC name here will be what? What will be the IUPAC name that nobody knows? Parent alkane, 1 carbon is methane. You have 2 chlorines, so it would be dichloromethane. No one knows this compound by its IUPAC name. So we need to know the methylene chloride is the dichloromethane. The next one that people use is that. The most common one is chloroform, and chloroform is this. So the most common one is CHCl3, called chloroform. Thankfully, chloroform is now taken off the list, but people still talk about chloroform. You know, we're not allowed to use any of these things, but if you go to grad school, they're gonna let you use them, because by that time, they don't care about your safety. When you're in graduate school, go right ahead. And then the very last one, which is CX4, the other very, very common is CCl4. CCl4, you're gonna be seeing me use it a lot. So CCl4 is called carbon tetrachloride. Okay, so this guy is carbon, bless you. 2 words, carbon, often called carbon tet. So if you get to grad school, they call it carbon tet, but it's really carbon tetrachloride. The reason why I'm saying you have to know these names is because from now on, when we have all of these reactions, that's going to be the name that we're using. We're not using the IUPAC name. So these are the names that we're using. I think it makes sense the way they are, but there they are. Methylene, all right. Common solvents, methylene chloride, chloroform, really? Carbon tet, really? All right, here we go after all that time squeezing these names. All right, let's see how we're going to classify the alkyl halides. So the chemistry of the alkyl halides, we're going to, all of the reactions, the first thing that we need to do is to classify them. And by that I mean, you're going to look at the type of carbon. If all you have is a methyl, it's called a methyl halide, and we abbreviate methyl like this. So we're going to say, oh, it is a methyl like that, methyl halide. We put the little methyl and the little circle at the top. Or it could be a primary alkyl halide, and then we use the number 1 with a little circle. I hope you're not copying all of this. Or the secondary, that you will have the 2 and you put the circle by it like that, secondary. Or tertiary, I'm not watching you copy all of this, because you're gonna identify them quickly. Okay, or tertiary. So, that's all we need to know. It's either a methyl, a primary, secondary, or tertiary. And so let's see if we can classify them. Here we go. Methyl halide, you can see what it's saying. A methyl halide, it's a halogen bonded to only 1 carbon. So when you have a hydrogen only bonded to 1 carbon, that's called a methyl halide. When you have a halogen bonded to a carbon, and that carbon is only bonded to 1 carbon, that's called a primary halide. When you have a halogen bonded to the carbon, and that carbon is a secondary carbon, meaning bonded to 2 carbons, that's called a secondary halide. And then the last of the story, when the carbon is tertiary, then the halide is also called tertiary, right? So that's the first thing we're doing for any of the chemistry that we're about to do. Rule number 1 is identify the halide. Because depending on the halide, it will be also the chemistry that you're gonna do, okay? So, and from this day on, every time we get into a functional group, I'm gonna say, this is going to be the way that we should envision learning the material. So the alkyl halides and the alcohols the same, primary, secondary, or tertiary. So, all right, and I think everybody knows what this is, right? And if not, the discussion packet has a whole question just dedicated for you to identify primary, secondary, or tertiary. We do have dihalides meaning 2. There are 2 dihalides when you have 2 of them. And it is important that you see the difference, okay? It is important that you see the difference. Again, all we're doing is putting foundation to the chemistry to follow, right? So we're just creating a little network to get there. We can have halides on the same carbon, and if they're on the same carbon, they're called geminal. How many people are here Gemini, like twins, on the same carbon? That's geminal, on the same, so you can have geminal dihalides. I don't know why they're calling it here. They're coming up with a specific example where you have the dibromide, so that's a geminal dihalide. Or you can have them on neighboring carbons, so you can have them on neighboring carbons, and on neighboring carbons, you use the word vicinal, really from the Latin for neighbor, vicino, which you are neighbors. So, good example, if somebody says I have 1,1-dichloro, immediately you know that that's a geminal dihalide. 1,1-dichloro, or 2,2-dichloro, or 3,3-diiodo, 4,4-dibromo, those are geminal, on the same carbon. Vicinal would have to be a 1,2-dibromo, or a 2,3-dichloro, or 3,4-diiodo, so they're on neighbors, one next to each other. Again, based on the chemistry that we are to see soon. Okay. If I continue with this, yes. This is for enjoyment. This is for enjoyment. This is if you end up getting on Jeopardy in the future, or I don't know, what's the millionaire questions? I don't even know what's the name of the show, but there's a millionaire somewhere. Huh?
Who wants to be a millionaire?
Okay, who wants to be a millionaire? So if you, or the other one, who's smarter than a 5th grader or something like that. All these shows where they're testing your memory, yeah. So here's for that. This is, my point is this is not gonna be on the test. My point is this is not gonna be a test question, how's that? So they were used as household cleaners. A lot of these compounds that we're seeing, the alkyl halides, were used as household cleaners. No longer able to be used as household cleaners. A lot of them are now on the carcinogen list. Chloroform is toxic. Carbon tetrachloride was used in the, when you take your clothes to the laundry, you know, like if you were to take your clothes to the laundry, carbon tetrachloride was used to take out any kind of organic stuff like you got on it, food that is mostly also organic, piece of steak meat. It was carbon tetrachloride. They cannot use it anymore, so they've come up with something better for them too, you know, for them too, not just for us. They were used as anesthetic. Chloroform was used as anesthetic. You know the Old West, the wild Old West, when they used to put the mask over your nose, that it was either ether or chloroform. It's a carcinogenic and it's toxic. All right, so now they're using a mixture of halides. Now they have better than that. They're using Versed that will put you on the subconscious, you know, conscious sedation. So all that is not used anymore. They were used for anesthetics, not anymore. They were used as freons, they were used as refrigerants, but then you know the story, they started to take away the ozone layer, so they had to be discarded. And then they also were used as pesticides. DDT, everybody knows the terrible stories with DDT in World War II and around that area. So all of these were the uses, all of them are gone. So they still end up being used for our solvents in the lab. So they're used a lot for solvents in the lab. All right, dipole moments, I absolutely hate this stuff, but here we go. Dipole moments, does anybody know what a dipole moment is? I think the dipole moment is that the change in that electronegativity value, you know, so it's measured to see what it is. So we're gonna be looking at the electronegativity of the halides. Everybody remember the trend, electronegativity goes from bottom to top, meaning fluorine is the most electronegative. It has a value of 4, bless you, has a value of 4, followed by chlorine, which is 3.0, I think that is bromine at 2.8, and I don't remember what iodine is. Okay, but that is the trend. So the most electronegative is fluorine, and it goes from bottom to top. Okay, we need to know that. That is the trend. I think we've drawn periodic trends already in another slide someplace some time ago. So based on that, right, you would think that the one that has the highest dipole moment will be a carbon-fluorine bond, right? Yes or no? That's what I think. I mean, if you're the most electronegative, then that, you know, that dipole moment should be greater, okay? A moment in English, okay, the bond length, wait. Okay, so sorry, I went too fast, I don't remember these things. If you're looking at the bond length, okay, the smallest is fluorine, so you would be expecting that the carbon-fluorine bond will be the smallest, right? And as you go down, I'm not liking what I'm saying here. I'm not enjoying this. Forgive me, not enjoying this. So not enjoying this moment here. Okay, periodic trends. This is how I've memorized periodic trends. I went ahead and I drew, oh, you're mid. Looking at periodic trends, if I come over here and I draw a, right, I always used to say when I taught Chem 10 or so, Chem 1, and I have to look at periodic trends. I'm really interested on group number 7, the noble gases don't play. And I also said in order for me to mail you a letter, I need to put a stamp or the post office will not mail it for you. My stamp is fluorine. Fluorine is the most electronegative atom in the whole periodic table. So electronegativity increases this way. Pink is electronegativity is increasing this way, right? So for us right now, you know, when all of them are here, chlorine, right? We're studying these guys, and then we have bromine, and then the very last one that we study is iodine. We're doing the chemistry of these 4 elements only. Chapter Chapter 6 is only the chemistry of these four bonded to a carbon atom. That's it. Okay? So pink is electronegativity. Electronegativity is that way. Negativity, that's what that says. That's electronegativity is increasing towards fluorine. And just like electronegativity is increasing that way, atomic size is the total opposite of that. So atomic size is increasing going down and going this way. This is atomic size. Complete opposite trend. Complete opposite trend to your electronegativity. Okay. Everybody okay? Okay. I hope everybody remember these periodic trends because they will show up at every chapter. They show up every chapter. Okay, so here's the start. Based on that, fluorine is the most electronegative. Based on that, this is the smallest bond, distance-wise, I would assume that the carbon-fluorine bond would have the highest dipole moment, right? That's what I would assume. Well, when you look at the dipole moments, this is the beginning of a switch in a trend. I would call this, I'm sorry, I hope I don't offend anybody, but I had a really hard time learning English because in Spanish, when you see the vowel A, is A everywhere, that sound A is the same. And in English, I had the hardest time saying why is apple, apple with an AP, and then why is April with an AP. So this is one of those moments. Why? Cannot be explained. The carbon-chlorine bond has a larger bond dipole moment than a carbon-fluorine bond. So this is a break in what we expected, right? So the expected here is not quite the same. So the carbon-chlorine having a larger bond dipole, a lot of chemistry that we'll be seeing is with the carbon-chlorine bond. So the majority of the chemistry that we're seeing is carbon-chlorine, carbon-bromine, carbon-iodine. Carbon-fluorines, we hardly do any chemistry in it. Fluorines are not good leaving groups, okay? They are not good leaving groups. So, sorry, a break in the trend, Okay, and the molecular geometry, it depends on that. For example, when you have somebody like carbon tetrachloride, that you're expecting to follow all of that, carbon tetrachloride, even though you're going to have 4 carbon-chlorine, carbon-chlorine, carbon-chlorine bond, carbon tetrachloride is actually a non-polar molecule. So in order to decide if you have a polar molecule or not, you really are having to look at a bond, right, that you have a polar bond, but the rest of the molecule, right, the rest of the molecule cannot, right, overcome that polarity. So we really are hoping to just deal with the chemistry of just one carbon to one halogen bond, all right? So that's all we're gonna be looking at. All right, boiling points. What do we know about boiling points? Well, okay, here's a trend for boiling points for all of you, okay? The greater the intermolecular forces, the higher the boiling point. I hope everybody knows that. The greater the mass, so they're saying that the dipole-dipole attractions are not significantly different, meaning, and I don't remember any of this really, so if you don't want to copy, you don't have to. I'm not really big on this at all, and I have to get to something that I will remember, okay? So here's what's something that I remember. Greater mass, higher the boiling point. So if somebody were to say, if you're comparing 1 carbon and 4 chlorines, or 1 carbon and 3 chlorines, the expectation is what? The 1 carbon with the 4 chlorines would have a higher boiling point than the 1 carbon with 3 chlorines. I'm not big on this kind of trends. They really will become very important. These trends of boiling point, melting point, density, they would all become very important when you're comparing one functional group to another, right? So the only thing that I can get to, is that if you have comparable molar masses between an alkyl halide and an alkane, is everybody with me? People are saying, I'm tuning her out, she says it's not important, like why pay attention? One moment, periodic trends, alkanes and alkyl halides. Which one would have the higher boiling point? Comparable molar masses, that means you cannot compare one compound that has a molar mass of 100 to a compound that has a molar mass of 40. Not okay. We're comparing 100 perhaps to 98. Molar mass, that's a comparison. So 100 versus 98, alkyl halides or alkanes, who would have the higher boiling point? Everybody? If you have an alkane is somebody like carbon, hydrogen, carbon, 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 hydrogen. Okay? So if you have carbon, 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 hydrogens, all like that, and over here you have carbon, carbon, halogen, the expectation is that this molecule, comparable molar mass, would have a higher boiling point. At least you have dipole-dipole, right? So you have dipole-dipole. That's where we're going to be using all this. I'm not going to be comparing two alkyl halides to one another. I mean, I have a table for that, right? We all find these things on Google. Shh, nobody uses tables anymore. Google that, right? All right. So here's the only thing I'm going to remember. Okay, here's the only thing I'm going to remember. And this is an important trend. Check this out. What does this mean? What does this mean? I need to know that. This I need to know. How does this guy look? This guy looks like I have a carbon, and I have a Br, and I have a carbon, and a carbon. Are you seeing this? So this is a methyl. I'm going to just write it a methyl, a methyl, a methyl. What was this guy called in? This was terbutylbromide, no? This was terbutylbromide, and this is why. Isn't that? 1, 2, 3, and one more carbon. Okay, so the one on the left, I don't want to make this complicated. This one on the left is terbutylbromide. And this one on the right is what would have been called N-butylbromide. Right? Everybody there. Terbutylbromide, N-butylbromide. Will be the name between the two. Yeah? So, what is really, really important is that the more spherical, if you can have the compounds like in a nice little ball, they would have a lower boiling point than the big chains that are doing the wave. Okay, these chains are doing this wave, and that wave, the attraction between these atoms are making this be difficult to break apart because they're like this whole thing. So straight, the spheres would have a lower boiling point. Comparable masses, right? They both have the same mass. These two both have the same mass. What are these guys? Isomers of each other. Okay, so they're isomers. If you put them into a sphere, their boiling point is lowered. Okay, that's what I would remember. All right, when we're looking at densities, forget it. We already did this. They're denser than water. I'm not going to remember this. All right, and let's take a look at preparations of alkyl halides. I'm looking at how can I make alkyl halides. You will have the beginning of pink sheets on Wednesday. I don't know if I talked about pink sheets or if you've heard about pink sheets. Did I tell this story in this class or no? Okay, so this is a historical moment in my life. When I came here to work at Solano College, all the handouts were in white, and perhaps they would give you a blue piece of paper. You know, that's how it was. Or yellow, I think it was yellow. Those are the only colors that were here. I had lived, this is what I say to everybody, I had lived in a blue world for many years. I had a husband and 2 boys for many, many years. And then I got pregnant and I had a daughter. And that's when I said, that's when pink came into my life. And then I started teaching here, and that's how they became pink color papers. It wasn't for anything else, but other than it was significant for me that now everything was pink in my house. All right, so that's how pink became pink. And so I had pink before Victoria's Secret brought pink. But no joke, she had no clue that it was pink and I was using pink. The pink sheets for me was like this paper that I will give to you, and we have them for every chapter. So here we are in Chem 4, and the students just got this pink sheet, which is aldehydes and ketones. Take a look, that's number 7. So there's like 12 of these before the year is over. But then you carry this with you instead of your book, you know, that we could all carry this with us. So every day to class, I would bring it and bring your pink sheets, and we're working out of that. So it became really, really good to study. They are so famous that when I retire, I'm just gonna go ahead and spend time and publish them. Because I get people from everywhere. I'm in Berkeley and I heard of your pink sheets, would you mind sending them to me? So, it's just a way to remember. So the very heading of the pink sheets will be preparations of alkyl halides. Where and how can you make them, right? Have you made alkyl halides already? Yeah? Yes? Where have you made them? You're right, don't.
Chlorination.
But yeah, we went ahead and I think the PowerPoint is gonna help us out. That did not help me out at all. That doesn't help me out at all. This kind of helps me out, but that still doesn't help me out either. Yikes, this is just no good. No good, no good. All right, so here we go. So I'm gonna start with how many ways do we know how to prepare. So my pink sheet will begin with preparation of alkyl halides. And the only one that I have done is from alkanes. So we have done chemistry from alkanes. And from alkanes, all we did was your free radical. All we did was free radical, either chlorination or bromination of alkanes. That's what we did. So if we come up with a specific example, in my specific example, we have this. And we react this with chlorine, and we do light. All we know is what? You know so much already. How many equivalent hydrogens do you have here?
All equivalent.
Equivalent hydrogens in cyclohexane are, all of them are equivalent. So it doesn't matter which one you picked out. You would have ended up with something like this. And your HCl, and we don't have to go anymore through that whole story of what were the steps of the mechanism. We did that already. Is everybody? Oh, you needed to have the initiation step. Oh, you had all the propagation step. Oh, I'm over that, right? We're over that. All we're after is that, oh, I know how to make a chloroalkane. Is everybody? I know how to make a chloroalkane from cycloalkane. Yes? I lost somebody, what's going on? So this is your chlorocyclohexane. We don't have to call it a 1, all you have is 1. Even though she wasted her time, this is achiral. You don't have to draw it as R or S or none of the above. So we could do chlorine, or we could come over here. And if we do bromine, and we're looking for the major product, what will be the major product over here? You're looking at the major product,
The tertiary carbon.
which would be your tertiary, which we would have that, and your HBr. So the only thing I know how to make from alkanes is everybody, so if your chemistry is from the alkanes, the only thing you can make is a chloroalkane or a bromoalkane. We do not know how to make a fluoroalkane, or we don't know how to make an iodoalkane. It's everybody. We do not. This is it. Limitations. Okay. Your PowerPoint was even super nice in saying, I used some of the examples that the PowerPoint did, and in the PowerPoint they picked that. Only 50% that they found was that chloro. We don't know what the other 50% was. I don't know if it's multiple chlorinations or not. In the case of the isobutane, 90% of the products analyzed was your tert-butyl-bromide. So, this is the only thing we know. Chlorination is not selective, so if you wanna make a primary, a secondary, a tertiary, perhaps you can. We do know that depending on the temperature, too many limitations, is everybody, too many limitations. So perhaps bromination is the best, where your tertiary carbons are highly selective. You know, the secondaries are first, the primary, meaning if somebody gives you a structure like I just gave you, right? If anybody gives you a structure like I just gave you and they ask for the major product, be looking for the tertiary carbon. Everybody, be looking for that tertiary carbon is what we're saying in here. Everybody okay? All right. Let's talk about this other allylic bromination. I think I'm gonna draw two because I like my way better than this thing. So let's take a look at an allylic bromination. First of all, what the heck is allylic? Let me give you an example of allylic. I have a carbon double bond. Anything on that carbon-carbon double bond would be vinyl. If you go one carbon away, so you need to be one carbon away from the double bond, this is your allylic position. Okay, so that's allylic, one carbon away. One carbon away from the double bond. Is the allylic position. Right. Oftentimes, the better way to look at this is in a ring. For example, if I come over here and I do a ring, and I put my double bond on the ring, how many allylic positions do you have? Is everybody seeing that you have two? This carbon away is allylic, and this is also an allylic position, right? So you can look up or down.
So a question, so say you had a benzene ring, which has like 3 double bonds, would all of them be considered allylic, or because they're attached to other double bonds, you can't have it?
You can't, it would have to be a carbon out. Good point, I'll answer that in a minute. So when you're looking at the two carbons, everybody saw immediately that you would have two allylic positions. The next thing you really want to see is, are all these hydrogens now equivalent, right? So you have really like 2 hydrogens here and 2 hydrogens here. So definitely it looks like it doesn't matter, right? It looks like it doesn't matter because if you substitute any one of these for a bromine, it's called an allylic bromination. If the bromine is here and we don't know how to name this one, this guy is called cyclohexene. The name for this one is cyclohexene, like that. Cyclohexene will be the parent. When you go ahead and you put a bromo here, this will be actually 3-bromocyclohexene. If you put it here, if you put it down here, it will be 3-bromocyclohexene. I think the point I'm making is that all the pink hydrogens are equivalent. Okay, all of the pink hydrogens are equivalent. If you look at the N-bromosuccinamide, it's going to be the one compound that we're going to be tracking. For this to work, NBS is called NBS. You don't even need to know how it looks like. In Chem 3, all we're interested is that NBS has only one Br dot. That's it, one bromo. There's only one bromo in N-bromosuccinamide. I'll show you the picture momentarily. And in order for this to work, you need to have it in presence of light because it's going to be a free radical. That's all we want you to know right now for this class. We don't want you to know any more than that. But when this happens, you would go ahead and be replacing one allylic hydrogen for a bromine. Now watch what I'm doing here. Oh my gosh. So, all you're doing is replacing one allylic hydrogen for a bromine. What exactly does this mean? Well, let's name the compound first, okay? Let's name the compound first. You know that alkenes is also gonna be on this exam, right? Alkenes is in the next exam. So we're creating a new layer of nomenclature, and the new layer of nomenclature is naming alkenes. Naming alkenes, the alkenes are gonna be the parent. And because the alkenes are gonna be the parent, the compound parent will be called cyclohexene. And as a parent, you need to have the lowest number. So your options here are only this. I'm either 1 and 2, your alkene is either 1 and 2, cyclohexene, we don't have to number it, or your alkene is gonna be 1 and 2, cyclohexene, right? We don't need to use them. If I go green, all of a sudden this is carbon 1, carbon 2, 3, 4, 5, 6, that'd be 6 bromo. What the heck? Why don't you go with pink? If you go with pink, that'd be 1, 2, 3. So this compound is gonna be called 3-bromo cyclohexene will be the name for that compound. That's it. 3-bromo cyclohexene.
Would you
Yes.
include the RNS?
Oh, yeah. All right. So the first thing is 3-bromo cyclohexene. Is everybody okay? You do not have to call it 1-cyclohexene, because you only have 1 double bond, and it's already understood that I was gonna be carbon number 1. Is that carbon chiral, number 3, is that chiral?
Yes.
Yes, it is. Would you be able to assign R or S? I don't wanna hear it. I want everybody to have the time to do it. I don't wanna hear it. Don't wanna hear it. I wanna hear people being able to do it. R or S?
R.
Is everybody seeing R? Yes? If everybody's seeing R, I'm moving on. You don't see, okay, so here we go. The decision of why is it R, okay? The BR is the highest priority, that's priority 1. The hydrogen is 4, okay? When I look at this carbon, I get to this carbon here has only 1 hydrogen, while this carbon has 2 hydrogens. So use that, the carbon that has the least number of hydrogens means that it has the more substitutions. Instead of worrying about how you break the double bond, just simplify your life, okay? If you only have 1 hydrogen, that means you're more substituted than the carbon that has 2. Is everybody seeing that? It's like this carbon is bonded to really 3 carbons, to 1, to 2, to 3, and then the hydrogen. So that's priority 1, over here is 2, here is 3. You're going that way, and you're staying because the lowest is in the back. So for this to be perfect, you would have to come out here and call this R, 3-bromo.
You wouldn't have to put 3R.
You wouldn't have to because there's no other chiral carbon there. If you put 3R, I'm okay too. I think R or that. Kylie said something really, really important, and she mentioned something about the benzene rings, right? So she says, oh, okay, well, what about the benzene rings? Well, the benzene rings have all these double, 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 single, double, single, double, single. So right now, there's no allylic position, because 1 carbon away from the double bond, you have another double bond, okay? But if you move outside of the ring, and over here you have 3 hydrogens. Now this carbon is 1 carbon away from a double bond. Is everybody seeing that? So this carbon here, there's a double bond, 1 carbon away from the double bond is what we have been calling your allylic position. So if this reaction, if you had your NBS and light, there should only be 1, 2, 3, 4 products, what would you have? We're not doing chemistry in the ring. There's no chemistry in the ring, so the chemistry would still be outside of the ring. You keep all your double bonds the way they are. And this is your product here. Not chiral, this compound is achiral, and that will be the only possible product that we're expecting. That's it. We don't know how to make alkyl halides from anybody else. We know from alkenes, we know from alkynes, but we're not in those chapters, right? So we're not there yet. So let's take a look at the chemistry of the alkyl halides. Let's take a look at the reactions of alkyl halides. I do like the PowerPoint slide. I do like this slide, and because I do like this slide, I want to make sure that we spend a few minutes on it. We're going to be tracking actually two types of reactions of alkyl halides. There's going to be two types. I think you can see that if we have an alkyl halide, and this is the representation of an alkyl halide. So if you have an alkyl halide, and that alkyl halide is reacted with a nucleophile, the nucleophile actually can replace the halogen, and we're calling this a substitution. So when you sub the halogen for a nucleophile, you end up producing a whole new set of compounds. That's called a substitution reaction. You're replacing a halogen for a nucleophile. But if instead you bring in a base, the base perhaps could have removed that hydrogen, and if it's removing that hydrogen, it's end up producing an alkene. The halogen takes off, okay? So when you lose HX, because really it looks like I've lost HX, that's going to be called an elimination reaction, where you only form your carbon-carbon double bond. All right, so I do not want to taint what we're going to be seeing in the future, so I don't want to give you my own personal opinion of all of this. The most important thing about this chapter is the mechanism, okay? How exactly does this occur? All right, so how exactly does this occur? I will be naming alkenes, and I think I'm going to add that today to the day in Name It this afternoon, mostly because we're such a large class that I think we can do it all, okay? So I think we can do it all. So I'll be finishing the handout for this afternoon at 12, and I will be putting it on Canvas for all of us to know what we're going to do this afternoon. But it is dry lab, so if you have your open toes, you're okay. So let's see how the beginning of this, let's see what the PowerPoints here are helping us with. Let's talk about this SN2, first story about SN2. What does it stand for? I don't like it. I like my papers better. Sorry. I don't like it. I do not like it. All right, so we're going to call this reactions of alkyl halides. And we're going to be looking at specifically substitution reactions. So we're looking at substitution. We're going to categorize it as SN2. S for substitution. N for nucleophilic. Two for bimolecular. Okay, so SN2, substitution, nucleophilic, bimolecular. The first thing that happens in a substitution nucleophilic bimolecular is your substrate. Your substrate is going to be your alkyl halide, that's the substrate. The alkyl halide is the substrate. This does a terrible job, okay? So in this example, my alkyl halide is gonna look like this. I'm gonna have a carbon. I am going to have an iodine. I'll have a hydrogen, and a hydrogen. First thing that I'm going to do is I'm going to identify or classify. So let's classify. What type of alkyl halide is this?
A methyl.
Tertiary?
Methyl.
It's a methyl halide. All you have is a carbon. So you have a carbon with a hydrogen, that's a methyl halide. I'm gonna bring in a nucleophile. I'm gonna call this hydroxide, it's gonna be my nucleophile. Hey, I don't buy hydroxide like that, but anyway. You know, I buy hydroxide as sodium hydroxide. But hydroxide, I'm introducing you to its name, as if you didn't know. Hydroxide is what I'm gonna call my nucleophile like so. Remember how I put that picture like that? At the end of this reaction, what's gonna happen is I am going to substitute the iodine for the nucleophile. And when I draw it, I'm gonna show it like that. So I'm representing that I switch the orientation. When before your iodide was pointing to the right, now the OH is pointing to the left. And at the end of that, I'm gonna have the I minus. The I minus is gonna be called the leaving group. Leaving group, which in this case is iodide. And this new thing is my new product. For you guys, this new product is an alcohol. You don't have to know how to name it, that's all you need to know. Your new product is an alcohol. So this is when you're gonna start using the knowledge of your functional groups. We're done, time to go. Yikes, this was